Today we want to look at how to calculate the speed of a wave. Realize the answer to this question depends on where the wave is found. Sound waves, light waves, water waves, they're all going to have different formulas. Today we're going to focus on the wave traveling through the string of a musical instrument. The same thing we did in lab yesterday. We'd now like to formally make sure we understand what's going on. So yesterday we looked at the strings on a guitar. We sent a pulse down the string and we timed how long it took the energy pulse to reach a certain space. Based on the distance it traveled and the time of travel, we were able to find speed. So don't forget the formula for speed that we've been using since the beginning of the year. Speed equals distance over time. Okay, we tried using identical strings, but under different tensions. So this guitar is going to be strung with just two strings that have exactly the same linear density, but one of them is going to be stretched until it reaches a tension of 90, and one of them is going to be stretched until it reaches a tension of 40. When we send the two waves down the string, we're going to find that it travels faster when the tension is higher. So that's our first thing you want to make sure you know. Waves travel faster through a string when the string is under more tension. The looser the string, the slower the wave is going to travel. When we graphed this out, it turned out not to be proportional. It turned out to be a square root relationship. That means in order to get the velocity to double, we need to have the force tension get 4 times bigger. Okay, so tension and speed are not proportional. Doubling one does not double the other. You need 4 times the tension in order to double the speed. Okay, what we didn't test yesterday was what happens if both strings are at the same tension, but one of the strings is heavier than another. It turns out that when the string is heavier, the wave is going to move slower. So when we take a look at this thing, the wave is going to travel slower under the heavier string. Okay, when we put this all together, we get a formula that looks like this. Speed of the wave is equal to the square root of tension on top, linear density on the bottom. Linear density, just to make sure you're clear, is not regular density. It's not mass per unit of volume. It's mass per meter. It's how much mass there is in a meter of string. Okay, so what you want to do here is these are grams per meter. You'd want to move it over 3 spots and get it in kilograms per meter and put that in on the bottom of your fraction. That'll let you know how fast the wave is going to travel. You'll notice when we look at the waves being made in these ropes, they travel really slow. It's because there's usually not a lot of tension in the rope. You don't usually pull it taut. And the rope is usually really heavy. Both of those factors tend to slow down the travel speed of the wave. Okay, so you could almost run faster than that wave. Okay, the speed of the wave is not important in and of itself. We don't really care how fast the wave is traveling. However, it's real important because it's the first step to figuring out what note is going to come out of a stringed instrument like a guitar. So if we want to produce a certain note, we need to make sure we know the speed of the wave. All right, so that's why we learned how to figure out the speed of the wave. We're not going to learn how to turn it into an actual note until after the break. Okay, so string number 1, lots of tension. String number 2, a little bit of tension. Which one's going to travel faster? Now I've got 2 of them that have the same tension. One is heavy and one is light. Determine which one is going to have the wave, the pulse of energy, travel faster. Okay, and then mathematically, I'd like you to try just one of these. It says a violin string has a mass of 5 grams. It has a length of 1.2 meters. It is strung until the tension reaches 80 newtons. Remember, the bottom is called linear density, and you might want to find that first. So linear density, you do mass over length. You put in your mass in kilograms. You leave your length in meters. You get one number, and that number gets plugged into the bottom of your equation. You then use the tension, which is 80, the number you just calculated, and you solve for the velocity. Most times the velocity is going to be a pretty high number. These wave pulses are moving really quick. It's going to be really hard to see them without a super high-speed camera. We want to know how long it's going to take to travel from here to the end of the board and back again. That's going to be a round trip distance of 80 centimeters. So once you have your velocity, put in 0.8 and solve for time. How much time does it take the wave to travel from one end to the other?